And the things that we are being asked, actually, we're only being asked to find one thing. We're asked to find how much is there in 1,000 years. I believe this is the question that you guys were asking about. So we've got some radioactive isotope that's decaying. We know there's initially 10 grams. And then we're looking at how much would there be after 1,000 years. Not a lot to go on. I would agree, right? Like, it feels like there's just not enough information here. So besides all of this, tell me what you do know. Tell me what you know. Is there anything else that we know besides the fact that this thing has a half-life of 1,620 years, whatever that means, and that initially there are 10 grams? What else do we know? Come on, people. Anything at all. Anything at all. Hey, Tim, by the way, you are going to be our guinea pig for if that mic works. So you're going to have to give me some feedback. Chloe, give us something you know.
Well, Cole said the half-life is the amount of time it takes for the initial amount of grams to be cut in half. So, like, at 5 grams, it's 1,620.
Ah. So you're saying after 1,620 years, or 1,620 years, then we would only be looking at 5 grams remaining, because that's what half-life means. It's interesting. Other stuff that you know, or they could be things that you wish you knew, or it could be other making sense of things. Doesn't really matter to me. Trevor, what else you got?
Well, I would say that it's probably going to be an exponential decay function, since it's decaying.
Yeah, it's a radioactive element. It says decay. I mean, all of these things actually, so elements actually decay exponentially, especially radioactive ones. So we're looking at some kind of exponential decay function. Now, I really just have to make a choice. Do I want to look at this as an annual decay? And I'm going to go ahead and put this down as a recipe, because that's how I see kind of, once I identify that it's exponential, I can get the generic structure of the equation, and that's kind of a recipe for me, so I don't have to do so much craziness at this point in time. It's kind of breaking it up so I can find little things. So I can either view it as an annual decaying situation, which it's not really, because it's not like the radioactive isotope just sits there, and then at the end of the year it goes, boom, oh, look, I broke down a little bit. You know what I mean? It doesn't do that. It's breaking down all the time. Or I could actually look at it as a continuous compounding situation, which I know what continuous compounding looks like. Now, again, one is actually probably more applicable. The continuous compounding is really what's happening, right? Because it's breaking down all the time. But in theory, you can model any exponential function as either, and it doesn't really matter. And we saw this when we looked at compound interest. So we just have to make a choice. And since I'm the one doing the problem, I get to make the choice. I'm going to choose this one, just because I want to see us using this one. Plus, it also kind of goes along with some of the feedback you guys gave me on things that you wanted. Okay? So I'm making a choice. All right, so let's go ahead and let's use this structure, because that's really important. Let's use this structure to start plugging some things in. Is there anything that I know already about my equation? Is there anything that I know? Yeah, Mitchell.
Well, since you know the half-life is 5 grams, you can kind of put that in to the equation, put that in for y, and you can just plug in 1,620 years as your time.
Yeah, and that's awesome. So you're saying, like, look, this is really just a t value, and this is really just a y value. So I could really say 5 equals PE to the r times 1,620. Oh, still a lot of variables. No. Come on, people. Yes, Tate.
That your initial amount is 10 grams, so you can plug that into P.
Yeah, and I'm going to do that right away. So I know that the initial amount is 10 grams, so that's really my P. So really, this is the structure of my equation. And then what Mitchell is saying is that we can go ahead and we can put these numbers in there, right? And ultimately, if you think about it, what's the thing that we really wish we knew at this point in time about this situation? What's the thing you're like, oh, if I just had that, it would be done? R, which is really the what? The rate. We wish we knew the decay rate, but I don't. So Mitchell's saying like, we don't know the decay rate, but we do have a data point. So let's plug in that data point there. 5 equals 10 e to the r times 1,620. And if we look now, there is only one variable left, r. And Kristen had said, I wish I knew what r is, so let's just go ahead and solve for it. First step, if I was solving this, what would you do, Gabe?
I'd probably put it into a log.
Now, I could if it was simply an exponential. It's not yet. What's tripping us up from having just an exponential equation? Regan? Yeah, that 10's kind of annoying. Let's get rid of that first. And then the beautiful thing is that's going to leave us with, 1/2 equals e to the 1,620 times r. Now, I want you to think about this for a second. That equation makes a lot of sense to me. Half life, you see that half? And then 1,620. Makes sense. Okay, so then Gabe said, let's put it into log form. I like that idea. The exponent is what I'm looking for. So let's put it in the log form. So it'd be log base e of 1/2 equals 1,620 r. Or I could just write it as natural log of 1/2 equals 1,620 r, because that's really what log base e is. Again, I'm doing that for those of us that aren't comfortable with that idea yet. And then if I'm looking for r, pretty simple. I'll take care of the hard step. Here we go. Divide both sides by 1,620. And I'm sorry that didn't show up all the greatest. I'm going to get rid of some of my extra stuff going on over here. What does that give us as the rate? And I'm going to want lots of decimal places here. And I don't have a calculator sitting by me, so if you could grab that for me, that would be great. What do we get as r? I don't know if I put it in right because she goes, it's negative. Why does that make sense? Because it's decay. It's decay. We're decreasing. So, wow, yeah, that is a small number. So we get negative 0.00042788. And I'm just going to put a 9er on there. So really, if we look at it as percentage, it's like negative 0.042789% per year. So it's not losing a ton. Now keep in mind the reason we wanted r is so we could complete our equation. So now we have y equals 10 multiplied by e to the, and I'm just going to write r there because I don't really want to write that big long number, but I can. Wait, I'm done, right? This is what I was looking for? Oh, wait, what? I have to plug in 1,000 years. Right? Because that's really what I was looking for. So I'm just going to go ahead and do y equals 10 times e to the, again, remember r is actually a number. I'm just choosing to just label it rather than actually, rewrite it because that's annoying. And I would just type this in my calculator and I would be done. Because I'm looking at the rate for 1,000 years. And Trevor's got it, which is why he's looking at me, and he's going to go ahead and give me that value.
6.52 grams, I believe.
And it's always a good idea for us to ask, does that answer make sense? Does that answer make sense? Fist means I'm thinking. Thumb up means I've got a thought and why it makes sense. Thumbs down means I have a thought on why it doesn't make sense. Does that answer make sense? Cole, why do you feel like that answer makes sense?
Because the half-life is 5, and that's very far away from that, so it's not super far away from the 5, but it's obviously bigger.
Yeah, we haven't reached a full half-life yet, so we're going to have more than just half of what we initially had. But we're not that far off, so we're not going to have like all of it still remaining. So that seems to make sense. It's in the ballpark, So we can't discredit that as being the answer. Okay?